Welcome everyone to the last talk today. It's by Lauren Williams from Harvard. Who's going to talk about Grassmannians and Amplituhedra. And for the local participants, we're going to have a wine reception afterwards.
Thank you so much. It's great to be here virtually, although I would vastly prefer being in at the Isaac Newton Institute. I'm going to speak about the positive Grassmannian and a generalization of it called the amplituhedron. And the way I'm going to structure these lectures is that lecture 1 and 2 will discuss the positive Grassmannian, and lectures 3 and 4 will discuss the amplituhedron. So I'm going to start very slowly, and most of what I say in lectures 1 and 2 is sort of fairly old and well known in these circles. But anyway, so the Grassmannian, GRKN, is the space of all k-dimensional subspaces of an n-dimensional vector space. And I will represent points in the Grassmannian as the row spans, of a full rank k by n matrix. And I will often refer to this matrix. I'll often use the notation C for the matrix. And then we have coordinates on the Grassmannian. So for I, a k-element set of the numbers 1 through n, will let P sub I of V be the k by k minor of C using columns I. So this is called a Plücker coordinate, and this gives us a map V into projective space, where the projective coordinates are all of these n choose k Plücker coordinates. This gives a map into projective space of dimension n choose k minus 1, and it embeds GRKN into this projective space. Now I want to say right away that, there's a bit of an echo. I don't know if that could be fixed by, okay, good. So I want to say right away that I'm often going to identify matrices with their row span when I talk about elements of the Grassmannian. So let me just say that once and for all, and that I'll abuse notation like this when I'm talking about the Grassmannian. So let's do a small example. Let's let C be this 2 by 4 matrix, which I'm identifying with its row span, which is a 2-plane in a 4-dimensional vector space. And now if we compute its Plücker coordinates, P1, 2 of E is the determinant of the matrix, the 2 by 2 matrix in columns 1 and 2. This is 1. P1, 3 is 2. P1, 4 is 4. P2, 3 is 1. P2, 4 is 2. And P3, 3, 4, which is the determinant of the submatrix in columns 3 and 4, is 0. Okay, so this is the Grassmannian and its Plücker coordinates. And now I want to talk about something called the matroid stratification. So the matroid stratification of the Grassmannian is the decomposition of GRKN into strata based on which Plücker coordinates are non-zero and which are 0. So I'll just partition them into groups based on which Plücker coordinates are strictly 0 or non-zero. So for example, if we go back to this matrix C here, 5 out of 6 Plücker coordinates are non-zero, and the coordinate P34 is 0. So so continuing this example, C lies in the stratum where P34 is 0 and all other Plücker coordinates. Delete this instead of having recopied it. So above, C lies in the stratum where P34 is 0 and all other Plücker coordinates are non-zero. Okay, so so in my lectures, we're going to take always GRKN is the Grassmannian, is the real Grassmannian. And when we're talking about the real Grassmannian, there's a theorem of Mignoff, the Mignoff causality, which is that a matroid stratum can have topology as bad as that of any algebraic variety. So when we partition the real Grassmannian into strata based on which Plücker coordinates are non-zero versus 0, we get strata with a very bad topology in general. And this is actually the basis of a paper by Ravi Vakil called Islamic geometry. The upshot is that matroid strata are topologically very bad. Okay, now let me start talking about the positive Grassmannian. So we say that an element in the real Grassmannian is totally non-negative, which I'll sometimes abbreviate as TNN, if up to a global change of sign, all Plücker coordinates are non-negative. And similarly, we'll say that V is totally positive, or TP, if all Plücker coordinates are strictly positive. And now I'll let GRKN greater than or equal to 0 be the set of all points in the Grassmannian where Plücker coordinates are non-negative. So it's the set of all totally non-negative points in the real Grassmannian. And similarly, I have this notation to denote the set of all totally positive points in the real Grassmannian. And these two, well, so this first object in particular is called the totally non-negative Grassmannian, or sometimes informally just the positive Grassmannian. Okay, so let me give a little bit of history behind these definitions. So the totally positive and totally non-negative matrices were studied in the 1900s by a number of authors, including, for example, Gantmacher, Krein, Whitney, many others. And then in the 1990s, Lustig revisited the theory of total positivity when he realized that one can define the totally positive and the totally non-negative parts of a real reductive group G, or a generalized partial flag variety G mod P, in such a way that the totally positive part of the general linear group recovers the set of totally positive matrices. So he has several papers from the 1990s about this, and Constance Reach also wrote several papers about this. She had been his PhD student, and in her thesis gave cell decomposition of the non-negative part of a generalized partial flag variety. And then somewhat independently in the early 2000s, Postnikov gave an independent definition of the positive Grassmannian, and his definition was the definition that I gave above. It's not obvious. It's not obvious, but his definition agrees with Lustig's in the case of the Grassmannian. And this was checked in an email sent by Connie Reach and was written down subsequently, giving different proofs in a paper with Kelly Talaska, and several other references have also verified that these definitions agree. Okay, so so now let me say a little bit more about what happens with the totally non-negative Grassmannian when we think about the stratification. So, and this was part of Postnikov's early motivation. So while matroid strata of the Grassmannian have bad topology, if one intersects them with the positive Grassmannian, then one actually gets topological cells. So let me write down this theorem, which appears in Postnikov's 2006 preprint on the subject. So if M is a collection of k element subsets of the numbers 1 through n, then let's let Sm be the set of all points in the positive Grassmannian where the Plücker coordinate pi of v is strictly positive if and only if I belongs to this collection. Then each non-empty stratum Sm is a topological cell that is an open ball. And if it is non-empty, then we'll call M a positroid and Sm a positroid cell. Okay, so I mentioned that that Reach in the 1990s had given a cell decomposition of the non-negative part of G mod P, and her cell decomposition agrees with Postnikov's in the case of the Grassmannian. So in this lecture, I'm going to explain some of the combinatorial technology developed by Postnikov to discuss the cells. So this is from his preprint, and what a main goal of his was to classify these cells. So to show that they are cells and to classify them. So this, he shows that positroid cells are in bijection with various nice combinatorial objects. And the one that I will focus on today is move equivalence classes of Plabic graphs. And another object that I will talk about in the next lecture is decorated permutations. So yes, so I will now start talking about Plabic graphs, and I'll just mention that that what I'm discussing today is you can find this material in Postnikov's 2006 preprint, and you can also see a recent exposition in chapter of the cluster algebra book that we've been writing jointly with Fomin and Zelevinsky. Okay. Okay, so let me tell you about these Plabic graphs. So a graph is a planar graph G in the disk with n uncolored vertices on the boundary labeled 1 through n in order, let's say clockwise order, such that the following properties hold. And actually, let me draw a picture so that you look at it as I continue with the definition. Okay, so we already see we have a planar graph in a disk with n vertices on the boundary labeled in clockwise order. And we're going to also impose the requirement that each boundary vertex is incident to a single edge, and each internal vertex is colored black or white, and moreover, each internal vertex is connected by a path to some boundary vertex. So I don't want to have some sort of floating component of my graph inside of the disk. I want every vertex in my graph to be connected to the boundary. So that's the definition of Plabic graph. And And if I have a boundary vertex I attached to an edge, which is a leaf, we'll call it a lollipop. So this right here is a black lollipop. And in general, in these talks, we will assume that G has no internal leaves except for lollipops. Okay, so these are the class of graphs that we'll be looking at. And these graphs come with some local moves. So for example, there is the square move, which is also related to an operator called urban renewal. And in this square move, if my graph contains a local configuration that looks like this, meaning I have an internal square in which all internal vertices are trivalent and colors alternate, then I have a local move which allows me to replace it with the local configuration which looks the same but colors are swapped. So that's one such local move. And I should say that since many of you here work on cluster algebras, these graphs and this local move are closely related to cluster quivers and quiver mutation. There's also a couple of sort of more trivial moves. So there's a merge, unmerge move. And here, if I have a univalent edge, so if I have two vertices of the same color connected by one edge, then I can sort of squash that edge while preserving everything else. So the only requirement here is both vertices must have the same color. And then we can also remove two valent vertices of color. So if I have something like this, I have this two valent black vertex, I can always remove it, or conversely, I can add in a two valent vertex wherever I like. So these are local moves that our graph that we want to consider on the set of all Playbit graphs. And then we say that two Playbit graphs are move equivalent, and we write G equivalent to G prime if G and G prime can be related by a sequence of moves M1, M2, M3. And then one more definition I want to give, which is that a Playbit graph is reduced if there doesn't exist any graph G prime move equivalent to G such that G prime contains two adjacent vertices U and V connected by more than one edge. So things like this are bad. Okay, maybe I should pause and see if there's any questions based on the definition so far. Okay. All right, so now I want to explain how to use these graphs to encode cells. So let's let G be a bipartite playback graph in which each boundary vertex is incident to its vertex. So I'll draw a small example here. Another way you can think about this is that we have a bipartite graph in which I think of the boundary vertices as all being colored black. And now we say that an almost perfect matching M of this bipartite playback graph G is a subset M of edges such that each internal vertex is incident to exactly one edge in M. So yeah, so it's a perfect matching in the usual sense, except I don't really care about whether boundary vertices are matched. And then I'll use this notation, partial M to be the set of all I a boundary vertex, which is incident to an edge of M. Okay, and so I started by imposing this hypothesis that G is bipartite, and let me just mention that by using move M3, we can always add and remove two valent vertices of either color, and so we can always arrange for our graph G to be move. I mean, every playback graph is move equivalent to something which is bipartite, so I can always apply moves to make my graph bipartite. Okay, so let's do a small example. So if G naught is this graph here, then the almost perfect matchings are as follows. So I have this perfect matching here. Well, I guess I'm calling them almost perfect matchings. And then there's also this one.
There's a question in the chat.
Uh-huh. Do you want to read it to me?
I have a big echo.
Oh, okay. Let me take a look. Is being reduced a property of the playback graph G or of the move equivalence class? good question. Being reduced is a property of the move equivalence class because because I say a playback graph is reduced if nothing in its equivalence class has a bad configuration like one of these. Okay, so these are the almost perfect matchings. And in this case, if M is this matching right here, then I would say that del M is 1 and 2, because 1 and 2 are the boundary vertices touching one of the edges from my matching. So now there's this nice proposition relating this combinatorics to positroid cells. So let's let G be bipartite, and let's let M of G be the set of all boundaries of almost perfect. Then if this set is non-empty, then this collection of k element subsets of 1 through n defines a positroid cell. So let's continue our example. So if so 1, 2 is the set of endpoints of this perfect matching. This is 1, 3. This gives 1, 4. This gives 2, 3. And this gives 2, 4. And so we get M of G naught is 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. And so this data labels the positroid cell where precisely these Fluker coordinates are strictly positive. And the matrix we were looking at before exactly had P34 is 0 and all other Pij being strictly positive. And so this represents a point of this positroid cell. Okay. So so these playback graphs encode the data, encode descriptions of positroid cells, but one can do more than that. You can use them to actually parameterize the positroid cells. And the result I'm about to, so I'll say Postnikov used playback graphs to parameterize positroid cells. The way I'm going to write down the following theorem is not exactly how he initially wrote it down. I should say that after Postnikov's work, there was work by Talaska giving a kind of nice formulation for Fluker coordinates, and also subsequently a paper of Spire interpreting Postnikov's results, or this parameterization of positroid cells, as a variant of a theorem of Castellan. So, so the formulation I'm giving is closer to the spirit of how Talaska and Spire wrote down this sort of result. So let's let G be a bipartite play-bit graph with n boundary vertices 1 through n. And let's think of them as all colored black. We want to make sure we're dealing with a graph that has at least one perfect matching. So we'll suppose that G has at least one perfect matching, M0. And let's let K be the cardinality of del M0. It's the number of endpoints which are incident to an edge of our perfect matching. This number is independent of which matching we chose. Now let's let W be a map from the edges of the graph to positive real numbers. We're going to call this a weight function. And W sub E denote the weight of edge E. And then if M is a perfect matching, we'll let weight of M be the product of the weights of all edges matching. Okay, so the statement is that there is a K by N matrix L depending on our weight function and representing a point in the positive Grassmannian such that the ith Plücker coordinate is the sum of the weights of all matchings such that del M is I. And moreover, the set SG, which is set of all of these weight matrices, as the weight varies, is a positroid cell. Okay, so just to summarize, if we have a graph with at least one perfect matching, then we can arbitrarily put a weight function, positive real function on its edges, and this this gives us a weight on matchings, and then this weight on edges gives rise to a point in the non-negative Grassmannian whose Plücker coordinates can be computed using the weight functions, the sum of the weights of all matchings that have boundary equal to a particular K-element subset I. So so to every weight function, we get a point in the non-negative Grassmannian, and if we let the weight functions vary and we look at all associated points in the non-negative Grassmannian, we get precisely a positroid cell. And a exercise is to find a weight function W on the graph G0 that I showed a moment ago to realize the matrix C as associated to that weight function W. Okay. Now, I think I have exactly 4 minutes left, so I'm going to make one remark about circular symmetry in this story. So the observation is that totally positive and non-negative matrices have a kind of circular symmetry. And so if C is a k by n matrix with columns C1 through Cn, such that this matrix represents a point in the positive Grassmannian, and if we let Ci hat be -1 to the k minus 1 Ci, then the matrix obtained by first column, wrapping it around and putting C1 hat instead, also lies in the non-negative Grassmannian. And so this circular symmetry is going to be important in what I do in the next lectures. And I'll just mention you can see it sort of manifested in the circular symmetry of Playbit graphs, right? These Playbit graphs are drawn in a disk with boundary vertices, and circular symmetry is reflected in the circular. So the circular symmetry of the non-negative Grassmannian is reflected in the circular symmetry of the graphs. So I will stop there.
Thank you very much for this very nice lecture. Are there any questions? Further questions? No, nothing right now. So again, you can leave questions in the chat, and hopefully someone will pick them up, and yeah, we can discuss them. So then let's thank Lauren and all the speakers of today.
Thank you.
And we continue tomorrow at 12 UK time.